So let's continue our lecture. So we have solved this example 513. It is the last numerical of open system, and after that 514 is also a problem of 5 chapter Sangel book. But I gave this numerical for a practice question for you people as a homework. So done it by yourself. If you have found any difficulty, you can contact me or can comments on the classroom tab. Okay, so let's start a new topic. uh, before learning the Carnot cycle, we have to learn some terminologies prior to that Carnot cycle. So when the video is coming, you are aware of that terminologies. Okay, let's start with the what happened, sorry. Okay, let's start with thermal engine reservoir. Yes, thermal energy reservoir, a body with relatively large thermal energy capacity that can supply or absorb finite amount of heat without undergoing any change in temperature, such as body called thermal energy reservoir. For an example, we have a heat sink like a river, like a sea. The mass is so big, so it can absorb all kind of energy without increasing its own temperature, hypothetically, without increasing its own temperature. So we can consider it as a reservoir for heat sink. Similarly, we can form a reservoir for the source too, like the sun have infinite amount of energy that they are uh, giving energy to the earth through its radiations, and it is not decreasing by anyhow. So we can consider it as a thermal energy source. So in a thermal energy reservoir, we have two kinds of formation. One is the source and one is the sink. The source is producing energy and it giving energy to the system, and heat sink is absorbing the energy from the system. So by the definition, a reservoir that supply energy in the form of heat is called source. One that absorbs energy in the form of heat is called sink. I adjust that format to the above line in PDF format or in PowerPoint slide I will giving in when I was sharing in the classroom. So let's move on. Heat engine. A simple heat engine is the engine which convert or required the use of some special devices called heat engine. All converting heat to work required the use of a special device. Devices are called heat engines. All that engines can be characterized by the following. They receive heat from the high temperature source, like we have discussed source, thermal source, like for an example, we have a high temperature source, solar energy, oil furnace, nuclear reactors. All these kind of energy required some reaction, but after result of reaction, they are producing a vast amount of energy. In the combustion, we have a, for an example of oil furnace, we have a reaction, we have a combustion, and due to the combustion of even of oil furnace or natural gas or coal, the vast amount of energy is producing in terms of heat, in terms of temperature. So we can consider that as a thermal source. Like in nuclear reaction, when the nuclear reaction take place, it's also produced tremendous amount of energy that needed to be controlled. So we have a nuclear reactors in for the power generation system, that based on the Rankine cycle, as well as for the military purpose. So they convert part of that energy, especially heat, to work usually in the form of rotating shaft. We already covered the example of rotating shaft in a piston cylinder device, like our IC engine, internal combustion engine, installed in the car or motorcycle, etc. They reject remaining waste heat into the low temperature sink, the atmosphere, river, etc. So we also cover the explanation of Rankine cycle for the power generation system, in which we are rejecting the heat in river or in the sea. I give an example of Hapco power plant, Bin Qasim K electric power plant. They are situated, or Canap power plant. They are all situated around the large heat sink, like in the rivers or in the sea. Canab is stored in the along the sea. Bin Qasim power plant also installed in the Karachi Sea, and Hapco also installed in the sea and also in the stream of river. So they all installed where they can reject heat energy into the heat sink, and the best heat sink is river and sea. And they can also reject heat into the atmosphere, but atmosphere, it is not very good conductor of heat. So the better one is it should be stored around sea or river. But the heat energy can also be rejected in the atmosphere. Our atmospheric air also considered as a heat sink, like the car engine, the generator, they are rejecting heat through radiator to the atmosphere. Now they operate cycle, like in this figure. We have a high temperature source like solar, like uh, thermal furnace oil, thermal power generation system like furnace oil, coal, nuclear reactors. They all are producing large amount of heat energy that considered as a source. Then the part of the energy convert into the work, and the part of the energy reject in the heat sink, low temperature sink, like in the river, sea, and or at atmosphere. So we have some abbreviation for the heat work, like for the high temperature source we have a abbreviation of QN. Work, for the work we have a abbreviation work net out, and for the heat loss around surrounding is Q naught. So now I hope you all aware of that terminologies and how the system will work, or any heat engine work on these principle, on these basis. We have a high temperature source, we either in the reaction or in the combustion, and the part of the energy converted into the work, that is usually a shaft power, rotating shaft, and that rotating shaft converts utilized in the form of, like in our car, motorcycles, or rotating a generator to produce electricity. Anyway, to calculate how much amount of energy is utilizing in the fruitful work, we have a terminology, thermal efficiency. Thermal efficiency tells us the efficiency of the system, or telling the how much the heat engine is utilizing the net heat into the work, and how much amount it losing in the surrounding or heat sink. So by the formula, simple, thermal efficiency is the net work output divided by total heat input. So in the figure you can easily, or first we just read out the definition. The fraction of the heat input that is converted to the net work output is a measure of the performance of the heat engine, called thermal efficiency. From this figure you can easily see that we have a source like 100 kilojoules. We have two systems installed over here, system 1 and system 2, to differentiate their efficiency of the systems. So we have, sorry, yes, we have 100 kilojoules of heat source, and the network output in figure 1 or system 1, there is a 20 kilojoules of heat is converted into the fruitful work. So by the thermal efficiency formula, we simply divide this 20 kilojoules to the total heat input, that is 100 kilojoules. So by dividing this, we get answer of 20% or 0.2. When we multiply by 100 for getting a percentage, we get 20% efficiency. Whereas 80 kilojoules of heat is lost in the heat sink or in the environment. It can be at the along the river or a sea or environment. Like in the Rankine cycle, we see that the heat is releasing in condenser, where the flash, after the turbine we have a flash steam. So we have two options, either to convert into the water and then again fed through a pump, or pressurized and then fed to the turbine. So by pressurizing gases, it is a very expensive method, so we lose all the energy in the flash steam and convert that steam into the water, and then that water is fed through pump to the boiler, and from the boiler to the turbine, and the cycle goes on. So in this way, practical system, that kind of energy is losing in the environment. Even in when we combust the different gases or coal, heat is also releasing in the boiler to in the surrounding or atmosphere. So in the particular system, we have not only one heat source, one heat sink. We can there will be multiple heat sink. Like major heat sink will be like river or sea, but the nominal heat sink can also be environment, because the steam is passing through pipes, and the pipes are in atmosphere, so some of the energy also releasing in the atmosphere. Yes, so let's move on. Right. So for the heat engine, we have a very short example 6.1, in which again the same what we have discussed in the last two slides. We have some small numerical over here. Heat is transferred over to a heat engine from a furnace at a rate of 80 megawatt. If the rate of the waste heat rejection to the nearby river is 50 megawatt, determine the net power output and the thermal efficiency of this heat engine. So we have to find out two things: the net power output and the efficiency. So here we need to understand one more formula for the network output. It simply derives in this way: like we have 80 megawatt of total energy, and 50 megawatt is releasing in the river like a heat sink. So when we minus this two energy, we get the work output. The simple in the definition, the net heat input is 80, 50 is lost from the 80. So how much the left is? 80 minus 50, that is 30 megawatt. Okay, so by this we derive the formula: W net is QH minus QL. Okay, so by this we will get W net, that is how much? 30 megawatt. And to calculate the efficiency, it is simple: 30, the network output is 30 and the QH is 80 megawatt. So when we divide 30 with 80, we get answer 0.375. So when multiply by this 100, we get answer of 37.5% thermal efficiency. So we get the answer like this, 37.5. It's very simple numerical. So this kind of numerical can come on the MCQs type questions. Not for the actual numerical should be solved. It is because it is just formula, putting formula numerical, and you get the answer on just by simple subtracting and divide with the values. Now after studying these terminologies, these heat engine or this heat source, sink, work output, thermal efficiency, utilizing in the second law of thermodynamics. And the second law of thermodynamics, defined by the Calvin Planck statement: First we read out the statement. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce network output. So by this definition, we already studied that it cannot be possible to convert 100 kilowatt, like for this example, 100 kilowatt of heat energy directly into the work without losing in the surrounding environment or heat sink. So definitely it is not possible, because when you combust, we don't have a perfect insulator. So when we don't have a perfect insulator in the real cycles or in the real world, so when we combust the gas or the coal, some of the energy will be released in the surrounding. So in this way, the 100 kilowatt, if we combust the 100 kilowatt of energy, and that cannot be converted into that 100 kilowatt work, some of the energy will definitely lose in the surrounding or in heat sink. So it is defined by the simple uh, Calvin Planck statement. That is, it is impossible for any device to operate in such a that uh, cycle to receive heat from a single reservoir and produce network output. Okay, for this example, it is impossible, it is wrong abbreviation. No heat engine can produce get the heat of 100 kilowatt and produce 100 kilowatt of work output. So in the second statement, no heat engine can have a thermal efficiency of 100%. Okay, when we divide this 100 into 100, we get answer 1, and the efficiency is 100%. So it is also not possible by the formula. So, or as far as power plant to operate, the working fluid must exchange heat with the environment as well as the furnace. So I hope you well understand this second law of thermodynamics statement. Before coming to the Carnot cycle, one more definition or one more uh, terminology we also have to study, that is reversible and irreversible process, because all the processes in the Carnot cycle are reversible. So first we have to differentiate between two things in the thermodynamics by the in the definition under the thermodynamics. So reversible process is defined as a process that can be reversed without leaving any trace on the surrounding. Okay, both system and the surrounding are returned to their initial state at the end of reverse process. Process that are not reversible are called irreversible process. So all these definition are well defined by this below pictures. Like in first picture, we have some kind of plate, and below the plate we have a roller. So when we move slowly, or when we move this plate slowly towards the wall, the water will rise, and when we repeat this action and pulling that plate again back into the position, the the water level will decrease and comes into the initial position. So in both two cases, the process will return to their in initial phase. Okay, without leaving any trace in the surrounding. So we can consider it as a moving boundary control volume, like for example we have done to calculate the work. So this is the surrounding, this is our system. When we move back and forth this plate, the water level rise and comes again into the initial position. So we can call it as a reversible process in thermodynamics, because there will be no trace in the surrounding. Okay, but in the right picture, when you move this plate abruptly or in a very fast way, you can see that water will disturb and make a ripples, and it form a phase shape like this. So when we get this plate into the it back into the initial position, the water still will be disturbed. So we cannot say it is a reversible process, because it is leaving a trace in the surrounding, or it is not completely comes into the initial phase. Okay, so we can call them as a irreversible process. In the real world, all the processes are irreversible, because when anything has happened in system, some of the energy will release, some of the energy will release to the surrounding. So no real cycle have a 100% reversible effects. All the real cycle are irreversible, but to simplify the system, we make an ideal system, and for the ideal system we can have a process like reversible process, as explained in this picture. Because even in this, if we move slowly, when the water comes into the initial position, still there will be water in the wall of this system. So in a real world, reversible process is not possible, but just to simplify the system, to idealize the system, we can say that the water comes back to the position when we move it very slowly, and consider the whole water comes into the initial position, so we can call them as a reversible process. But in the real world, the reversible process is not possible. So let's move on. We have a animation of Carnot cycle. So let's watch them and understand the Carnot cycle. After that, we will
Good day, ladies and
discuss the
gentlemen.
numerical
Today's
of
topic
the
is the
Carnot cycle.
famous Carnot cycle. So, what are the things that we need to know about this life-changing cycle? So first, well, it is an ideal heat engine cycle by a French physicist, Sadi Carnot. It utilizes heat energy transferring from a heat source to a heat sink. In addition, it composed of 4 reversible processes. The reversible process means direction can be returned to its original position. Also, it uses ideal gas as its working medium. And no doubt, this is a perfect engine. No friction between piston and cylinder walls, and no heat transfer between the surroundings and your system is considered. Now, let's discuss how this interesting cycle works by exploring its processes, the 4 reversible processes. So now, for the first process, process 1 to 2. This process is called isothermal expansion. Isothermal in thermodynamics means no change in temperature, or in other words, temperature is constant or not changing within this process. So what happens here is that the heat energy from the heat source is transferred into the ideal gas. As a result, the gas expands, which then increases the volume and decreasing the pressure. Now next, process 2 to 3, which is called an adiabatic expansion. Adiabatic in thermodynamics means that there is no heat transfer between surroundings and your system, or to put simply, all change in temperature is contained within a system, which as a result making the entropy zero. On this process, our volume increases and pressure decreases. Third process is the isothermal compression. So by compression, it means volume is decreased and as a result, pressure increases. On this process, heat energy from the gas is transferred into the heat sink. And finally, the last process. The last process is called the adiabatic compression. Since it's an adiabatic, all change in temperature is contained within a system, and our entropy is zero. Also, since this is compression, it means our volume decreases while our pressure increases. So that's it. That makes it a cycle. So now, let me ask you this. why Carnot cycle is the most efficient cycle? Mhm. Well, it's because Carnot cycle is a perfect engine. The processes are reversible, working medium is an ideal gas, and of course, the thermal capacity of heat source and heat sink is infinite, which makes no reduction to both during heat transfer, as we have observed, right? But for all those same reasons, it makes this cycle impossible to operate in our real world, as obviously those things don't exist. Well, of course, we should not forget that it contributed so much today. In fact, it is a model of our car engines like Otto and diesel cycle. And so that's it. Once again, this is Easy Engineering. See you again for our other easy and fun engineering topics. Easy Engineering, engineering topics made easy and fun for you.
So I hope you well understand by the Carnot cycle by this animation. Now moves on. Sorry. Yes. These description already covered in the video, so I'm not read out again. But simple. This is the theoretical heat engine that operates on the Carnot cycle was Carnot heat engine. The Carnot cycle can be executed in either closed or steady flow system. The Carnot cycle composed of four reversible processes. These are the four processes which already discussed in the video. Let's revise it again. Reversible isothermal expansion process. So you already studied this isothermal expansion in polytropic processes. What is isothermal expansion? The volume will increase without increasing the temperature. In isothermal process, the temperature becomes constant. So how it is gaining the volume when the temperature becomes constant? We are giving, you can see from this picture, we are giving heat to the system. So if we stick this cylinder to its in it it's stick this piston, the heat will increase the temperature. But if we move this volume, the if we move this piston, the volume will increase, and the expense of energy will convert into the work. Whatever heat is providing to the system, it converts into the work without producing any without increasing the temperature. So the temperature will be constant, and giving heat will produce work. That is isothermal expansion. The gas is expansion, so it is isothermal expansion process. The second process is reversible adiabatic expansion, in which an adiabatic expansion, we considered this, we are putting insulated wall in that position. So when we are putting the insulation, then there will be no heat transfer in all its walls, not only this wall but all in this wall we are putting with the isolation plate, so no energy can be released from the system to the boundary. So when we place isolator or insulate, when we place insulation, the internal energy of the system will decrease, and that internal energy will produce work further, and it will further expand. So that will be the reversible adiabatic expansion from process 2 to 3. Sorry. Then after going into the final form, final displacement, now we are putting some low temperature thing over here, like an ice or any low temperature, like opposite to that. In first process we are giving heat to the system. So for an example, we are putting stove here, and in this we are putting some cold water or any cold thing, low temperature thing. So due to that, the temperature will also decrease in the system, but we need to cap this is isothermal compression. So to maintain the temperature constant, the expense of heat releasing from the system will goes to do work, and the gas will compress. The temperature will not reduce, but the gas will contract and the volume will be decreased. So this is the isothermal compression. And after coming to this position, we are putting again the insulator, like for this example insulation. So no energy will again release from the system. So in that position, the energy will be not releasing. It is adiabatic process, but the energy that already it have, it reduce. So by reducing the sorry it the internal energy will gain the energy. So to gain internal energy, we have to lose something. So we are compressing this gas to its final position. So by doing all this process again and again, you can see that this piston will move to and fro, and we can easily convert this to and fro motion into the circular motion. Like I already placed one picture in lecture number 7-8. I think I just show this yes, just like this. In this picture you can see that the compression and expansion, the piston will move back and forth, and by this ring and crankshaft we can convert this to and fro into the rotation or in a circular motion, and that circular motion can be utilized to run any wheel, to by connecting any generator to convert into the electrical energy. Okay, so let's move towards our previous lecture, that is, so we need to open yes now. So now you can understand the Carnot cycle, that to and fro motion can be converted into the work or utilizing in a real world cycle. But the Carnot cycle is the all the processes are reversible, so it is not possible in the real world. So it is an ideal cycle. So all these processes can be we can place an PV diagram over here. Like from process 1 to 2, the heat is gaining into the system by any high temperature source. From process 2 to 3, we have a perfect insulator. No energy will be transferred to and from the system, but the volume will increase and produce work. And process from 3 to 4, the energy is releasing from the system, like applying any heat sink over here. Like I told, that any low temperature thing, like a river, like a sea, or anything which has a lower temperature than the gas inside the cylinder, so the gas will compress from 3 to 4, and again by putting the insulator, the gas will again compress to from 4 to 1, and the process will move on and goes on and on. So by this process we get a continuous rotation motion by attaching this to and fro shaft with the uh, pin and the crankshaft, connecting rod and the crankshaft, like I've shown in the uh, PNG image. So area under the curve 1, 2, 3, 4 is the work done by the gas during the expansion part of the cycle. The area under the curve 3, 4, 1, this 1, 2, 3 is work done by the gas during the expansion, like heat is given to the system, so the volume will increase. And the area under the curve 341 is the work done on the gas during the compression part of the cycle by putting any low temperature thing, heat sink. The area enclosed by the path of the cycle 1, 2, 3, 4, 1 is the difference between these two 2 and represent the net worth during the cycle. Okay, so the difference of between 2 from 1 to 3 and 3 to 4, we get the net worth during the cycle. The efficiency of an irreversible heat engine is always less than the efficiency of reversible one operating between the same two reservoirs. Like for any heat engine, we have a two reservoir, high temperature source and low temperature heat sink. We can call both as a reservoir. In this picture, it just telling us that the efficiency of reversible cycle always be higher than the irreversible cycle. Okay, like because the reversible cycle are ideal cycles and irreversible cycle as are real world cycles, the energy is releasing. We don't have a perfect insulator. When we are passing steam from boiler to turbine, we need to have a perfect insulator to not to reject heat into the environment. All the energy should better utilize in the turbine, but still we don't have a perfect insulator, so some of the energy will release in the environment. So it is irreversible. We have irreversibilities in the real practical cycle. So by due to this facts and losses, the reversible cycle efficiency always be greater than irreversible cycle. So the efficiency of reversible heat engine operating between same two reservoir are the same. Like in the picture, in first picture, the heat engine have an irreversible cycle and the efficiency is lower than 2. The second process is reversible cycle and efficiency is equal to NTH2 is equal to NTH3. So in third case we have again reversible cycle. So can it be possible that efficiency of irreversible cycle is less than reversible cycle? Yes, it is possible, and it is a fact. It is always less than irreversible cycle efficiency, always less than the reversible cycle. But when the reversible cycle efficiency again is equal to reversible cycle in the practical world, it is not possible. But when this kind of thing is equal, we can write these two as a reversible cycle. Okay, in this picture. But this can never be greater than irreversible cycle, can never be greater than reversible cycle, or even equal to reversible cycle. So all this notation are showing over here. The nth of the system is less than the reversible cycle. Irreversible cycle, it is not possible. No, it is showing the notation. The thermal efficiency of actual and reversible heat engines operating between the temperature limit compare as follows. Now they are comparing these reversible cycle or reversible cycle with actual values. Like for an example, we have a high temperature reservoir of 1000 Kelvin and low reservoir of 300 Kelvin. We have efficiency of thermal efficiency like 70% of reversible cycle, and efficiency of irreversible cycle is 45. Now it is correct, because efficiency of reversible always greater than irreversible. And again in this picture, it is impossible to have efficiency of 80%. Okay, so when the efficiency of reversible cycle is 70, so how the same system between these two reservoirs have a 80% efficiency? It is impossible. That's why it is written over here is impossible. No efficiency will be greater than reversible cycle when operating same heat reservoir, source and heat sink. Okay, these are the notation it is showing over here. And we get the formula of thermal efficiency of is W net upon QH. We can convert this formula into the temperature versus. I just write the derivation over here. Let's, yes, like we have formula of heat engine is W net divided by QH. Okay, and what is W net? Basically it is QH minus QL, and we have denominator of QH. Okay, now when we have, sorry, yes, when we open the denominator and numerator, sorry, yes, when we open the numerator and denominator, we have n is equal to QH upon QH minus QL upon QH. Okay, so now the QH will be cancelled. Now the efficiency formula will be derived like QL upon QH. Okay, okay, now the formula is derived, sorry, how to, okay, now we have the formula for in previous slides of efficiency W net over QH. We open that formula of W net, QH minus QL. We open the denominator with QH and QL. When we open it, this divided by this divided by this. So when we open this, the QH will be cancelled, and the formula becomes 1 minus QL upon QH. We should remove this. Yes, this becomes a formula. But to further simplify the formula, and for just calculating the efficiency of ideal system, we can directly write the QL in terms of temperature, like show over here. The formula is 1 minus T QH upon QL upon QH. So for an ideal system like reversible cycle, we can directly write QH in terms of temperature, because the formula of a Q, sorry, because formula of Q is mc T. So mass will be cancelled, and remaining thing which is left will be temperature. So we can directly write this, sorry, we can directly write this like 1 minus TL over TH. This is the temperature of heat sink, and TH is the temperature of heat source. Now by this simplified formula, we can easily calculate the efficiencies and whatever the work done and remaining unknown parameter, like to solve this above numerical. Let's solve this above numerical. A Carnot engine shown in the figure 6.48, it is comes from the Sangel book. I will show this figure 2 from the book Sangel in 6.48. Receives the 500 kilojoules of heat per cycle from a high temperature source like 652, and rejects the heat to a low temperature heat sink 30 degrees centigrade. Now determine the thermal efficiency of the Carnot engine and burden by the system. So let's solve this numerical, but before solving this numerical we will see the picture from the book. Sorry.